Titled Universality by Suryateja.
Good evening. I'm Suryateja. I'm from engineering physics. Today I'm going to talk something on universality, and most of the content of the talk I took it from a blog post by Professor Tanstow. Yeah. Given the laws of physics, you can predict the behavior of any system. I mean, if you have the laws of physics, you get the differential equations, and once you solve the differential equations, you know the behavior of the system. But things are not that easy. I mean, when you come to the applications, I mean, it's not that easy that you just take some equations, solve them, and get the behavior. It's basically because of some complications. The complications arise due to the nature of systems. The systems may be too complex so that you don't know the total number of equations that you should consider for solving the system, or maybe the system is huge such that the number of equations is very large and it's not possible for you to solve the entire system. So I'll take an example. We have Newton's law of gravity. It says it has such a inverse squared law of inverse squared force, and it depends on some property of objects called mass. And given the Newton's law of gravity, we should be able to solve the behavior. I mean, solve how the objects behave if you know. I mean, how the objects with certain masses behave if you know their masses, etc., and the initial configuration. So, if you have just two bodies, you can actually solve the complete system, write the equations, and solve the complete problem. And it turns out to be that the general solution of the system is conic, and the famous solutions of them are the elliptical orbits. I mean, so now when you go to more number of objects, for example, three objects, there's no closed form solution for that, and the solutions tend to exhibit a phenomena called chaos. I mean, the solutions are not that neat, and so we expect when you increase the number of bodies, we expect the solution to become worse. I mean, the situation to become worse. But the thing is that when you have large number of bodies, you can actually, the systems have regularity with them. That is, when the system has become so large, you have a more order that associated with them. So, and the order they get, the regularity, the patterns they get are like, they're not depending on the internal structure of the system. Irrespective of the microscopic constituents, you have some basic properties for the macroscopic system due to certain relations. I mean, due to the nature. I mean, the global structure as such. It's not. So, this fact that the systems is, to know the behavior of system, we just need to know the global properties, that is the macroscopic nature of it, without probing into the internal structure. This fact is what is referred to as the universality phenomenon, and we see this thing in several places. Like all nature has lots of universal laws. Now, but all the universal laws don't have precise mathematical justifications. Some of them you do have justifications, and I'll be discussing two of the most important, or what I consider important phenomenon, is the universality phenomenon, and one of them is the universality of the bell curve. Now, many things in nature tend to distribute themselves in a distribution which is a Gaussian distribution, the bell curve. It's like many real life variables. Like whatever you take, they have, if the population, the number of quantity, I mean, population of the thing, the size of the distribution is large enough, then you actually see that the distribution is a Gaussian distribution under certain conditions. But many real life variables are actually exhibiting that statistics. So the reason for this is basically due to two mathematical facts. One is called law of large numbers, and there is something called central limit theorem. If you have a variable which is an average of certain number of identically distributed random variables, then the average of this all the things is as the number of variables we are considering increases, the distribution tends to be normal. If you take large number of things and average them out, the average variable tends to be normal distribution. So because this fact, many real life variables have, due to the fact that they are some additive quantities of some independent factors which are having similar distributions, you actually have this Gaussian distribution for many real life quantities. And some thing regarding mathematics, you have one of the place you see the Gaussian distribution is, in number theory, is the number of prime factors of number of prime factors locally tend to be in a if you take for every number, find the number of prime factors, and at a point the locally the thing looks like a bell curve, the Gaussian distribution. It is modulo some technical these things, but it has relation with the Gaussian curve. And even it's really important, the fact that many variables tend to exhibit this Gaussian distribution is really crucial. And especially in the financial sector, based on this fact, they make lots of predictions, and so most of the financial profits, risks, and all these are much dependent on this law, the fact that they are distributed according to the Gaussian distribution. And yeah. So this bell curve is basically universal in the sense that we don't, whatever be the internal structure, whatever be the factors that are causing this, giving you the variable, like there may be several independent factors which give you the particular physical quantity, but regardless of the quantities, the systems tend to give you a Gaussian distribution. So that's the universality in the Gaussian distribution. Now, similarly, there are many other universal laws with regarding the statistics of digits and basically the real life data. There are many other statistics. Universal laws, something called Benford's law. But I'll go to some universality phenomena in mathematics and physics. I'll be talking about spectral distributions, and this is a very beautiful ideas. There are beautiful ideas in percolation theory. I'll not go into that, but I'll tell you what actually is the problem of problem of percolation theory. It's like you have a system which is the structure of which is dependent on a certain parameter like a temperature or something, and as you change the temperature, the parameter, the structure of the system changes. So it's like it changes from one phase to other phase, like solid liquid phases. So we try, and at the critical temperature at which the transitions take place, the structure of the systems tend to be, they have very nice properties. The structure at the critical temperature tends to exhibit some fractal nature. So that's why that's one of the problems they consider in percolation theory. And recently, the Fields Medal in 2010 was awarded to, and one of the guys who got the Fields Medal was working in percolation, and he proved a result considering the, dimension of the fractals that you get. So I'll now move on to the main part, the spectral distributions. Now, in physics, the problem of spectral distributions, the fact that there is something universal about spectral distribution started with this subject initiated by Eugen Wigner. And his problem was that to study heavy nuclei, you bombard some high energy particles and probe into the structure of the nuclei. To understand what's happening inside the nuclei or what is the structure of the nuclei, you bombard it with external agents like high energy neutrons. And based on the information you get out of it, like what kind of neutrons, what energy neutrons are actually passing through it, and what kind of things are getting repelled, and what kind of things, by studying the scattering, how the scattering distribution is, you can basically find the structure of the nucleus. So Wigner noted that the energies for which the neutrons actually pass through neutrons were absorbed. They are called some resonant energies, and they tend to repel each other. Like when you plot at what energies they are getting absorbed, this is something like the energy. I don't know what they actually mean by tending to repel, but it's like what scales they are what they actually mean. Okay, I don't know the physics happening there, but basically the distributions are in a certain manner, and to understand the distribution, we need to produce some models. But thing is that this distribution, you take different nuclei and find the energies at which the neutrons are absorbed. The spacing of the energies, the difference between the all these energies at which these neutrons are absorbed tends to exhibit a universal character. That is, regardless of the nuclei you are considering, all the systems have a similar distribution of the spacing between the energies, resonant energies. So to explain this, we actually need to from the laws of physics, to actually derive this, what we need is that we need to put in a Hamiltonian and find the eigenvalues of the Hamiltonian, and show that the eigenvalues are actually distributed in same way for all the regardless of the nuclei. For all these Hamiltonian, the eigenvalues are distributed in certain manner. But problem is that the system is too complex. The nature of nuclei, etc., is too complex, so that you can't actually find what is the Hamiltonian. So people come up with models. So Hamiltonian is basically a linear operator. So this guy Wiener produced a random matrix model. That is, he said that we can actually assume the generally to study an object, if it is too complex, we try to study the average properties of it. So he comes up with a random matrix model. That is, the Hamiltonian or the Hermitian operator, the linear operator there is a kind of, we may say, infinite matrix or something. It's not exactly correct, but it's an infinite dimensional, in the infinite dimensional Hilbert space. The thing is a linear operator, and we can assume it to be a infinite matrix. So what he says is that take random matrices, random large matrices, and see the distribution of the eigenvalues. And he says the distribution of eigenvalues of these random matrices will be the same as the distribution of the energy levels in the corresponding to the nuclei. Why actually this, this correspondence is not mathematically completely justified, but it's like this is an idea, motivating idea behind proposing such a model. So, what do you mean by random matrices? Like he said, consider random matrices randomly and see what is the distribution of the. Okay, consider matrices randomly and see what is the distribution of the eigenvalues. So, to actually say something is a random, you should have a probability distribution and what kind of matrices you are actually considering. So, Freeman Dyson comes up with a model called GUE. The matrices he considers are unitary matrices with a certain probability distribution, which comes up naturally from. There are some measures on natural numbers called Haar measures, and so basically there's a distribution, and with that distribution he calculates the eigenvalue distribution, the spacing, and he finds that turns out to be something like this, which matches exactly with the nuclei's the energy distribution of the resonant energy distribution. So not only this, it happens that this particular distribution matches up with lots of empirical spacing distributions. Like this is a spacing distribution of some timings between the buses that are arriving at a certain place. So in general, it happens that many spacing distributions tend to distribute in such a manner. So we don't exactly know why this universality is valid. What mathematical structure is making this happening, but it is. People see that it is true. Now, the most amazing part of it is that this distribution has connections with the most beautiful part of mathematics, the prime number theory. So, it's like prime numbers are, in a way you can say that there's this function called Riemann zeta function. It encodes the information about prime numbers in a way. It's like it is defined by some summation 1 by n power s for whenever it is valid. Other places it is analytically continued, and you get a function which is analytic except at s equal to 1. So studying that function, the analytic properties of the function will give you the properties of prime numbers. It's like, So, and it turns out that this function has some property of this function has connection with the same the random matrix distribution. Thing is that first of all, the zeros of Freeman zeta function, the places where the zeta function becomes 0 and the prime numbers are explicitly related by some formula like this. The pi of x is the number of prime counting function, number of primes less than or equal to x, and Li of x. These are some special functions in prime number theory. So this zeta function, in a way, it encodes all the information about prime numbers. So studying zeta function will give you the properties of prime numbers, and this zeta function has the connections with this random matrix models. So in a prime numbers have connections with this random matrices, and basically the zeros of this function are actually non-trivial zeros. There are some trivial zeros when you actually analytically continue. All the -2, -4, -6 are all actually the zeros of this function. The non-trivial, rest of the, complement them, you get the other zeros, which are called non-trivial zeros. And I'm complete. So these non-trivial zeros, people believe that all these non-trivial zeros lie on a single line on the complex plane, that is real part of s equal to half on a line, and it's still the biggest unproved result, but the proved result by Hardy and Littlewood that there are infinitely many zeros on this line. Now, let's Hardy and let's Littlewood. Now, take the distribution of all these zeros on this line and plot it. You actually get for the first billion zeros of zeta function on this line, you actually get a distribution like this, which is very much matching with the distribution shown before, the Dyson's distribution. So it's like the fact that they're connected in a way. I mean, this random matrices, some heavy nuclei and prime numbers. It's because of some structure that we don't necessarily understand. I mean, people are working on this currently. I mean, people prove the fact that this universality is valid for. I mean, the fact that the distribution is in such a manner is proved for lots of random matrix models. So, but and this in some way gives the motivation and says maybe it is true or something. I mean, is an indirect support. It's not. I mean, so the proper mathematical justification wasn't still known. I mean, isn't still known. So, not only this connections between prime numbers and this random matrices, there are all of the phenomena of, I mean, universal laws. People don't exactly know why those universal laws actually exist. I mean, what is the origin of those universal laws? So understanding them is a important part of research. And thank you.